All right, so this is section 2.6. We're going to prove angles congruent. This is the last section of this chapter. Here are our goals that we're going to go through here. I'll let you read those on your own. But those should be the things that we can accomplish once this section is complete. This is perhaps one of the first theorems that we're going to come across in the course. It says, just a reminder, a theorem is a conjecture or statement that you prove true. So going back to all our groupings of statements, we've talked about postulates as the things we cannot prove, but they are true. Theorems are things that we can prove and are also true. Okay? So we'll talk about how we can prove this statement here in a little bit. But it says vertical angles are congruent. This is something we kind of already mentioned or talked about. Whenever we draw two lines and they intersect, you're always going to get two groups or pairs of vertical angles. Angle 2 and angle 4 are vertical. Angle 1 and angle 3 are vertical. Okay? This here says vertical angles are congruent. That is a theorem that is very important to us that we're going to use probably hundreds of times throughout the year. But it's really the first proof that we can actually, or theorem that we can actually go through a proof for. Okay? It says when you're trying to prove a theorem, it is useful to take the hypothesis and conclusion apart. We've talked about this already. It says the hypothesis is the given, and the conclusion is the proof of your proof. Okay. One thing as we go through proofs, you will never ever in your proof use the theorem that you're trying to prove. So I'm trying to prove this. So nowhere in my two-column proof or my paragraph proof or whatever type of proof I'm using will I ever make an argument that something is true because of this, because I don't know this to be true yet until the conclusion of my proof. Okay? It's like using, if I'm trying to define what complementary means, and I say that, well, there are two angles that are complement to one another. That doesn't make any sense because I don't know what complementary is, and if I use that word in my definition, it just gets me in a loop. So it's the same idea with doing proofs. What you are proving is not known to be true until you are complete. So if you were to use that inside your proof, not knowing it to be true, you would not officially prove your theorem. As we talk about creating proofs, the one thing that we talk about is using vocabulary words. The one thing that we're going to find out is that when we recognize that we have vertical angles, or the word vertical angle shows up in a problem, you will never use the statement definition of vertical angles. You remember what definition of vertical angles was? It was when two angles share opposite rays, essentially. It says if this angle here, or this side of that top angle 1 is opposite ray to a side of an angle, maybe angle 2, and then the same thing happens for that side right there being opposite rays with that. When that occurs, you have vertical angles. And basically that definition is a creationism type definition. It shows you how they exist, but doesn't really give you any conclusions in regard to like congruency or equality or anything like that. Okay, not really great relationships existing inside that definition. Okay, so that being said, down here, when we see that vocabulary word, we're not going to use, we'll mention something, but we're not going to use definition of vertical angles. Okay, so the theorem, and this is something that I don't really like about our textbook, but it happens, and a lot of our things in mathematics are this way. We've talked about how everything in our course, and really all of mathematics, all of our statements or theorems, postulates, corollaries, lemmas, all that kind of stuff, are written as if-then statements. Well, this is not written as an if-then statement. Vertical angles are congruent. Okay? But we can take that information and we can actually rewrite it into an if-then statement. Okay? If I take vertical angles are congruent, and I can write it this way: if two angles are vertical, then they are congruent. Okay, that says the exact same thing, but now it's presented as an if-then statement. So when we have our given, remember, is the hypothesis. Two angles are vertical. Okay, the prove is the then or the conclusion. So I'm going to try to prove they are congruent. Now look at our statements over here in our actual proof. It says given angle 1 and angle 3 are vertical angles. Well, that's what this says. That's what our theorem says for our hypothesis. But we need, in our actual proof, we need things to talk about. We need specifics. Okay? So instead of saying two angles are vertical, they actually give them names, and it's associated. We see those show up in our picture. We say 1 and 3 are vertical. Okay? If we wanted to, we could have done the same problem and said like angles 2 and 4 are vertical, and everything would work out the same way. So it doesn't matter which group of verticals you choose. But when we take a theorem and try to pull it apart so we have a given and a prove for our proof, we need specifics. We need names of things to actually talk about throughout the proof. Okay? It'd be really hard to say if I didn't name these 1 and 3 and I just said, well, the vertical angle in my picture that is on the left here, maybe referring to that angle, and then compared to the vertical angle that's on the left, the one on the right, it's just really hard to word that where I can just say angle 1 and angle 3. That's so much easier. So we have specifics that way. And it says you prove, well, the prove was that they are congruent, and I don't know if it's a direct object or whatever that is, but it's referring back to the two angles. Well, in this case, then the two angles would be 1 and 3. So this here, this 100% matches this here. So we go through and we've got our statements already constructed for us, which is nice. They're saying 1 and 3 are vertical angles. That was given. Okay. Now this is, like I said, this is the one time where we see that vocabulary word, and we're really not going to, right now, write anything from it. Okay. We're going to look at angle 1 and angle 2. Angle 1 and angle 2, they're saying they are supplementary. Angle 1 and angle 2 are supplementary. And my hope is that you see that they both form that straight line. If you remember, two angles that are adjacent and they're non-common sides, so that would be a non-common side, and so would that. If they form a straight line, they are supplementary. That statement comes from the linear pair postulate, which I believe was identified in section maybe 1.8 maybe? Nope. 1.5. Two angles form a linear pair, then they are supplementary. Okay? And we're getting from our picture here that they're forming that linear pair. Okay? So 2 and 3 is the same idea. 2 and 3 is now looking at creating that line right there. So it's the same logic or rationale of why that's true. So if you don't want to write linear pair postulate again, you don't have to. You've encapsulated both those ideas right there with that statement. All right, so what do we do though? Okay, we introduced the vocabulary word. We just introduced the word supplementary. So we need to write down then, what does that mean for the two angles that we said are supplementary? Right there. Remember, when two angles are supplementary, they add up to 180 degrees. And that is detailed in the definition of supplementary angles. And that definition is the reason you know you can jump from that statement there straight to that statement. In the glossary, when you look up supplementary angles, its definition says two angles whose sum is 180 degrees. Okay? If you're a person that actually wants to write this out right here, by all means go ahead. Okay? Because that is the definition. But generally speaking, writing definition of whatever the noun is much easier in terms of quantity of writing than to actually write the definition. Okay, so we also brought in this word, supplementary, and then that should then relate to 2 and 3. So that's why we write angle 2 and angle 3. Okay, now those two steps always go together throughout any proof. And we'll see a handful of proofs in the next couple days that you'll see supplementary show up in the problem, and then you automatically, so if I said 1 and 2 are supplementary, I would automatically then jump straight to this blue statement here. They always are come in tandem, okay? If I see supplementary twice, I will always have 2 of these, okay? And if that's the case, then I'll always have this fourth step coupled. So what I'm trying to show you is that there's patterns here. And when we go through proofs, if you can recognize the patterns that existed in other proofs, they can help you navigate the current proof that you're in. What I'm going to do here, I'm just going to erase some stuff so we can see just statement number 3. All I want to do is focus on statement number 3. And what I've done is I've shown right now that 2 things are equal. They're both equal to 180 degrees. Okay? And I'll make a side note real quick about what you've done in algebra. In algebra class last year, you would say, y equals like 2x plus 5. And then you had another equation that said, well, y is equal to negative x plus 10. And the question is, well, solve for x. Well, what you did, these 2 lines, they intersect. That's maybe 2x plus 5. Negative x plus 10 might look something like that. And if I want to see where they are the same, at that point right there, whatever the x value is, the y values are identical. So you said, well, the y values have to be the same because they're both y here. So then that allows you to set these 2 things equal each other. And you come over the side and say, well, 2x plus 5 equals negative x plus 10. Go ahead and solve for x, 3x. Subtract 5 from both sides to get 5. X ends up being 5/3. Then you plug back in, you solve for y. You've done that. Okay, you've done that. That was called substitution. Another technique for doing this was called elimination. But you did substitution first. That's exactly what's happening right here. Instead of y, as we had over here, we now have these 2 values. And those 2 values are identical. So that must mean that the things that make the 180s also have to be identical. Okay? And that's where we see this next line, line 4. On the left-hand side, it's M1, measure of angle 1 plus measure of angle 2. And on the right-hand side, it's measure of angle 2 plus measure of angle 3. And because the 180s were the same, these have to be the same. That is substitution. And sometimes people might call it the transitive property. I'm going to talk about why it might be the transitive property. If I do it this way, if I say measure of angle 1 plus measure of angle 2 equals 180, and then my next line I could rewrite as 180 equals measure of angle 2 plus measure of angle 3. We could call this statement A here on the left. This would be B, this would be B, and that would be C. If you remember, the transitive property said if A equals B and B equals C, then we could say A equals C. So we could automatically say, and we've shown this with our middleman kind of approach here. If I cover those up, okay, so the 180s were the same, so they overlap. Well, if all 3 of these things are the same, then any 2 are the same. So I say 1 plus 2 is the same thing as 2 plus 3. So that's the substitution or transitive. property. Neither one of them is fine. If it's a drop-down window, only one of them will be there. So then that will be obvious to be which one you choose. So that's a pattern. So when step 2 shows up, step 3 will always show up. When step 3 shows up, step 4 always shows up. Okay. Now it might not be using the same angles. Okay, they might have different names, but the general procedure is the same. Now, when you do this, I look at that line right there. There is an amount that is on both sides. And that amount that is on both sides is a measure of angle 2. And this will be common when step 2, step 3, step 4 show up. Step 5 will be here as well. If that amount is on both sides, we might as well get rid of it because it's a balanced value. So we might as well cancel it out. And that leaves me with measure of angle 1 equals measure of angle 3. Well, when I remove something like that, it was the same. I don't know what that number was. That symbol stands in for a degree. All I know is that it shows up on both sides. So if I remove it from both sides, that's called subtraction. So that's fine. And that leaves me now with measure of angle 1 equals measure of angle 3. Well, that's a number equal to a number. Okay, it's a degree of an angle equal to a degree of an angle, which then allows me to say, okay, well, how do the shapes relate then? If I have equality in their measurements, then I have congruence in regards to their shapes. So going from equality to congruence is always the definition of congruency. Okay, and you can see then we started with what? We started with 2 angles being vertical. What we were able to conclude that those 2 angles were actually congruent to one another. Okay, so now that we've proven this theorem, anytime after this point, okay, so the point in which you watch this in class, any point after the conclusion of this theorem in class, and this proof in class, you can now say, when I have 2 angles that are said to be vertical inside a proof, you can automatically say, well, we know they're congruent. And somebody will ask you, well, why do you know they're congruent? You can reference them back to this theorem, or this proof of this theorem. So once we prove something in class, we can then use it whenever we need to thereafter. So this is a situation of that. Okay, now this is just a random proof. This isn't going to be, we're not proving a theorem here that we'll use later on. All this says, if you're given angle 1 is congruent to angle 4. Angle 1 is congruent to angle 4. That was my given here. 1 is congruent to 4. So I'm going to go in and we'll draw my congruency symbols in my picture. Okay. We were taught that once we write our given down, look for vocabulary words. So there are no vocabulary words in here. Okay. But now I look at statement number 2 and it says angle 4 is congruent to angle 2. Well, if I look at 4 and 2, they are those 2 angles there. Why are they congruent? What kind of angles are they? They're like angles 1 and 3 up here, aren't they? They're vertical angles. So, statement 2 here, I know 4 is congruent to 2 because vertical angles are congruent. That is what our theorem up here said. Okay? If we didn't have this theorem, what I would have to do inside this proof is these 6 steps to show that angle 4 and angle 2 are congruent in this new proof. But now, because I've previously proven that vertical angles are congruent, I can take these 6 steps and rewrite them right here in one step. Be more concise about it. And that's the benefit of knowing theorems, is that they're going to allow you to make your arguments more concise, more compact and shorter, and your explanations are going to be easier to explain to somebody. Okay, that is on the same level of you in regards to your knowledge of geometry. So then we'll look. So because 4 and 2 are congruent, 4 already had 1 hash mark in it, so 2 is going to have 1 hash mark in it. Okay? Now, if I look at this, angle 1 and angle 2, they're congruent. Well, why are 1 and 2 congruent? Well, right now, they're just adjacent. They're next to each other. So they're not vertical or anything, but look at what just happened. We just put a mark of 1 in both those. So if you remember back to when we talked about the transitive property, we said if we have just a bag of a bunch of things that are all the same, okay, and I reach into that bag and pick out 2 of them, then any 2 of them are the same. And that's really what we've got going on here. We've got to take a bag and we put angle 1, angle 2, and angle 4 in that bag. And this picture is showing us that 1, 2, and 4, because they all have 1 mark in them, they're all the same. So then pick out any 2 that you want. If I pick out angle 1 and angle 2, I can make that conclusion that they're congruent. That's the transitive property. Okay. Now, you can also do it this way, and I like to write it this way. Angle 1 was congruent to angle 4. That was step 1. Angle 4 was congruent to angle 2. That's step 2. If we do this, we can see that 4 is the middleman, and if it's the middleman, we can get it, we wipe it away, and we're left with 1 and 2 congruent. Okay? The next thing says 1 and 3 are congruent. Well, 1 and 3 are these 2. So I'll put a mark right there and put 1 in there. Now that one had 1 mark in it, and I can't change it, so this one has to have 1 mark in it. Why are they congruent? Because 1 and 3 are vertical. Vertical angles are congruent. Now, why is angle 2 and 3 congruent? Well, think about this. Again, now I've got this bag of 4 things. Angle 1, angle 2, angle 3, and angle 4. And I have said that each one of them is congruent. Each one of them has 1 mark in it. So all of these in this bag are the same thing. So pick out any 2 of them, and in this case we picked out 1 and 3. Or sorry, not 1 and 3. 2 and 3. And we can compare 2 and 3. Well, that process, again, is the transitive property. Okay. Now, we can see that that can happen by using these 2. If I say, now I have to do a little bit of kind of restructuring. So if angle 1 is congruent to angle 2, we can actually rewrite that as angle 2 is congruent to angle 1. There's the symmetric property there. Angle 1 is congruent to angle 3. If we put those over top each other, we see angle 1 is that middleman. Remove it, and it leaves me with 2 congruent to 3, and that's our new statement. All right, so this next one, similar approach. Okay, we're gonna write our given down. Angle 2 congruent to angle 3. Given. Okay, now so we write our given down, and we ask ourselves, is there any vocabulary? No vocabulary. So I'm going to go to my picture, and I'll put that mark and that mark in there, just so I know what are congruent, or what is congruent based off the given. And now I'm going to make the argument of looking at my picture and say, okay, is there anything my picture can tell me? And there's not a lot of things that our pictures can ever tell us. One thing we know that we can see from a picture is whether we got linear pairs. The other thing we know is that we have vertical angles. Those are really the only 2 things right now that we can decipher from a picture. Do we have vertical angles here? Is angle 1 congruent to angle 2? And it's because vertical angles are congruent. So angle 2 had 1 mark in it from this previous statement. So I can't go and change that. That's predefined. So then angle 1 has to match to that. So angle 1 has to have 1 mark in it. Are there other angles up there that are vertical? Angle 3 and angle 4, are they vertical? So I can say the same thing here. Angle 3 is congruent to angle 4. I'm just going to leave it all under statement and reason number 2 because 3 and 4 are also vertical. Now angle 3 has 1 mark in it. So angle 4 has to have one mark in it. And now the idea is if I've got that bag of things, and I just put them all in there, a bag of a bunch of equal things or congruent things, angle 1, angle 2, angle 3, and angle 4 are in this bag. Can I pick any two of them out and say that any two of them are congruent? Okay. So step 3, angle 1 is congruent to angle 4, and that reason, that idea that was described here with this bag of equal or congruent things, and picking any two out, is the transitive property. You can see that here by doing, again, some reorganizing of things. I'm going to have to go take this first statement that angle 2 is congruent to angle 3. Okay. Now I'm going to take this one here and say angle 3 is congruent to angle 4. Okay. And then let's just rewrite. So that would give me a new statement that 2 and 4 are congruent. So angle 2 is congruent to angle 4. Okay. Now I'm going to use this one. So I got 2 and 4, but now I'm going to look at this 1 and 2 one. So I'm going to say angle 1 is congruent to angle 2. Do you see how we can merge these two together? And then angle 2 is going to be my middleman. So now angle 1 and angle 4 end up being what's left over. And that, again, it's a transitive property, but it happens a couple times. Okay. Which is fine. Transitive property is something that can link. We go basically if A equals B, B equals C, then A equals C. But you can go if A equals B and B equals C and C equals D and D equals E, then A equals E. It doesn't matter how many links are in there. We learn it. The simplest stage of having 3 parts, but it can have as many as you want. All right, so that's the logic, that's the geometry of vertical angles, that's the proofs that show up here with vertical angles. Now we're going to practice this concept with our algebra. So you're going to see questions like this. They're going to give you an image and then say, okay, well, what is the value of x? So we have to identify a relationship. Well, what do you know about that angle right there in comparison to that angle right there? Well, per definition, they're vertical. So that means these angles are congruent. And if the angles are congruent, that means their measurements or their degrees are equal. So 3x equals 2x plus 40. Solve for x. X ends up being 40. Okay. Now, if x is 40, that would be 120 degrees. This would be 80 plus 40, 120 degrees. Right there, you can see, yeah, they're the same. So that makes sense. Now, something we can go a little bit further with, if those are 120, how does that angle and that angle relate to one another? They should be supplementary. So if they're supplementary, then that's 60 degrees. And these two, or these two, should also be supplementary. So that's 60 degrees. And because those two or these two are supplementary, and these two or those two were supplementary, what do you end up recognizing about those two? They're vertical and they're congruent. Okay? So these relationships that we find, one relationship in mathematics can never contradict or make false another relationship. So the fact that these are vertical will never contradict the fact that these two are supplementary or these two are supplementary. All right, so here's another one. So these two angles, again, are your verticals. So that one and that one are vertical. So then the equation you're going to write 2x plus 21 equals 4x. 21 equals 2x. Okay. What I would do most of the time, I would just rewrite this as 21 halves is equal to x. And leave it as that. All right, so a couple other theorems that are founded using logic that we saw when proving that vertical angles theorem is what we call the congruent supplements theorem. Okay, it says if two angles are supplements of the same angle or of congruent angles, okay, two angles are supplements of the same angle or of congruent angles, then the two angles are congruent. Okay, it can be wordy, but I think if you look at a picture, it makes a little bit more sense. What this is saying, so it says if two angles are supplements of the same angle. So to do a specific case, two angles here, we're going to actually talk about angle 1 and 3. Okay, it says 1 and 3 are supplements. Okay, and 2 and 3 are supplements. So when we talk about this, I guess I highlighted too soon. It says 1 and 3 are supplements, and 2 and 3 are supplements. So 1 and 2 are actually the two angles here that are supplements. Notice they're supplements of the same angle. It's the same angle 3. Okay, if that's the case, then the argument can be made that those two angles are actually the same angle, or they're congruent angles. Okay, and here's the logic. Draw a picture. Let's say I've got this angle right here, and it's supplement there. So let's say angle here is 120 degrees. So that would make this angle here 60 degrees. Okay, I'm going to tell you that this angle here is supplement to another angle. Well, that other angle has to be 60 degrees to be supplement. Well, what's that tell you about these two angles? They're the same. That's the logic here that we're trying to decipher and to understand. Okay, but we can prove this. Okay, I've got the given written here. So again, we took in the if part and we've put it into specifics for ourselves. So that's the given, and then the prove will be the then. Okay. Now, as we go through this, you're going to find out that this proof is extremely similar to what we've already done. Okay, so I'm going to write my given, and this is something that is going to be, it's going to transcend the entire course with our proofs. Once you get a hang of them early on and commit certain procedures to memory, and maybe not even straight to memory, but no, I remember seeing that at one point. I've got my notes. Let me go back and revisit those, jog my memory a little bit, and then help myself with my current problem. So here's what we do. We write our given, okay? Now, I may have absolutely no idea how I'm going to go about this problem, okay, and how I'm going to get to the proof. But if we go through those 7 steps I gave you a couple days ago, those 7 steps said write your given down. Did that. Is there vocabulary? Yes, there is. Supplementary. What does that vocabulary mean for these two angles? Well, that vocabulary means for those two angles that measure of angle 1 plus the measure of angle 3 equals 180 degrees. And that's the definition of supplementary angles. Again, like I said, if you wanted to write two angles whose sum is 180, that's the actual definition in the back of the book. Okay? Well, we got another vocabulary word, supplementary. What's that tell me about angle 2 and angle 3? It says the measure of angle 2 plus the measure of angle 3 equals 180. Now my hope is that this jogs your memory a little bit from what we've already done today. Look at that statement and that statement, and let's go back up to the question about vertical angles when we did that proof. Do we see that there were two statements that talked about supplementary angles? And then we made two statements that said, well, these two angles should have 180. And then what came from that? Well, we made this comparison that those two 180s were the same, so these things must be the same. So it's the same procedure. Come down here. These 180s are the same. So that means that there and that there have to be the same. Measure of angle 1 plus measure of angle 3 equals measure of angle 2 plus measure of angle 3. If we went back up to the vertical angles theorem and the proof of that, this would have been the substitution. Replace that 180 or that one with what it was equal to. All right. If you want to call it transitive property, I'm okay with that. But let's go back up to what we did next. Back up in the vertical angle stuff. We wrote this thing down, and then we looked to see if there was something on both sides that could be removed, something that was the same. So come back down to ours. Is there something that is the same on both sides? Measure of angle 3, measure of angle 3. That's the same. Now, the one kind of caveat that might be a little bit different sometimes is that you might see from time to time people do this. And they're just telling the audience that what I'm about to do is legal because the value on the left-hand side is identical to the value on the right-hand side. And that was skipped in that vertical angle theorem because it was already predefined our statements for us. But I like to add this, the reflexive property. And you'll see in Chapter 4 the reason from now till Chapter 4 I will try to kind of ingrain the use of the reflexive property because in Chapter 4 it becomes very, very important for us to understand. But now if I remove those, I'm left with measure of angle 1 equals measure of angle 2. And removing something from both sides because it was the same on both sides is subtraction. It's a property of equality. And the next thing is that's not what I wanted to prove because right now I'm just showing you two numbers are equal. I want to show that the angles, the shapes that those two numbers come from are actually congruent. So that's a quick jump. If I know that these are measurements, so that's a degree, it's referring to an angle, that's a degree of another angle, then I know that the shapes are actually angles and they have the same degrees, so that allows me to make the conclusion or the jump from equality to congruence, and its definition of congruency allows me to do that. Or you can say angles with equal measures are congruent, which is what the definition of congruency says for angles. But again, that's less wordy than writing that out. So sometimes people think this stuff over here, these reasons, are kind of cryptic, that there's not a whole lot of like understanding or it's not very detailed in our explanation. It's because we're trying to minimize the amount of writing we have to do. Okay, and basically what I'm saying is if you need to know what this is, then you have a resource of a glossary or whatever it may be that you can find these vocabulary words in that allows you to then see this thing here. All right, so the same thing happens with complements. Okay, so if I've got two angles that are complement to a third angle, then those two angles are congruent. So let's say I've got angle 1 here and angle 2, and then let's say angle 3 and angle 2. So if I say angle 1 is complement to angle 2, so let's say angle 1 is 50 degrees. Angle 2 then would have to be 40 if they're complement. Okay? Well, if angle 2 is 40, then down here it's got to be 40 as well. So what does that make angle 3? Angle 3 then has to be 50, and what do we then recognize about angle 1 and angle 3? They're congruent. All right, and that's all that's saying. If I got two angles that are complement to the same angle, and the two angles I started with are congruent to one another. The proof for this is identical, 100%. The exact same thing is here, except for when I see that word supplementary, it's going to be complementary instead. And where I see that number 180 and that number 180, it's going to be 90 instead. But this proof and this proof are almost verbatim 100% the same. So I'm going to leave that one to you to practice on your own. Next one here, pretty straightforward. If I give everybody in class a right angle and then grab any two of them, they're always the same. Okay, any two right angles are always congruent, and we usually verbalize that by saying all right angles are congruent. So any two that you choose would be congruent. Okay, I'm not going to prove that with you at the moment, just to save a little bit of time. Two angles that are supplementary and congruent makes then both angles a right angle. So let's say I know that they're supplementary. What do they have to do to be supplementary? Let's say angle 1 and angle 2 are supplementary. Let's say that's given. And angle 1 is congruent to angle 2. That's also given. Okay. Well, our vocabulary here says measure of angle 1 plus measure of angle 2 must equal 180. That's the definition of supplementary angles. Okay. Now, if angle 1 was congruent to angle 2, we also know. So I'm going to do some substitution here, and I can't substitute a shape for a measurement or a measurement for a shape. So I need to make sure that everything is in terms of measurements. So I'm going to make that turn into that by using the definition of congruency. And now I've got free will to replace either that with measure of angle 2 or this here with measure of angle 1. Doesn't really matter how I do it. But if measure of angle 1 equals measure of angle 2, I can take this line here and rewrite it. But wherever I see measure of angle 2, I'm going to rewrite it as measure of angle 1 because they're the same. So I can substitute that way. Now we see that how many measure of angle 1s you have. You have 2 of them. 2 measure of angle 1s equals 180. So a little bit of algebra there. I'll just call that combined like terms. Now you can say, well, let's divide. Measure angle 1 equals 180. Oh, not 180, 90. 90. So that was division, property of equality, and we divided by 2. So now if I've got an angle that I've just identified to have a measurement of 90 degrees, I can classify it as a right angle because I know the definition of right angles. Well, if angle 1 is a right angle, and up here we said angle 1 and angle 2 are congruent, then doesn't that make angle 2 a right angle as well? Okay, so if 2 angles are congruent and supplementary, then they have to be both 90 degrees, making them both right angles. Okay, I don't think that's a far stretch for us logically to think about. Okay, I'm going to tell you, let's kind of do this. Let's say, so we got a linear pair, and we'll tell you that these two angles, angle 1 and angle 2, are congruent, and they form a linear pair. Well, telling you that they form a linear pair is telling you that they're supplementary. Well, if 1 is the same as 2, then they got to be the same. The only way they can be the same and add up to 180 is if they're both 90. That's really the logic that we're going through here, but we're expressing it so there's a valid argument of why I know that to be true, and I just don't tell people or relay and say, hey, just take my word for it. Okay, there's a valid, succinct argument of that truth. Just some. I'll come down here and do a couple of these. Let's do these 33 and 34 with you because these are a little bit more difficult. There's a lot of relationships that exist here in 33 and 34 that you can use, some better than others. One thing I recognize is that that angle there and that angle there are vertical. Okay, so I'm going to write 2x equals y minus x. And it's true, that's a valid relationship. Now what stinks about that is there's 2 variables. And if I'm going to solve an equation with 2 variables, I need another equation with the same 2 variables. We need a system of equations. So that I'm not going to erase. It's not wrong, and I might use it, but it's not extremely helpful yet. Okay? So the next thing I'm going to do is I'm going to look at maybe these two. And that's going to allow me to come up with the equation that 2x, because these two are a linear pair, so you say 2x plus y plus x is equal to 180. Okay, well that can clean up to like 3x plus y equals 180. We want to do it that way. And that is actually enough that I can use these two. I can use these two with substitution or elimination to solve for x and y. Okay, what I would do, can I add x to both sides in this red one and get 3x equals y? And now use that right there and say, okay, well, y, because of this equation here, y is 3x. And I get 6x equals 180, so x will be 30 then. And if x is 30, then I come back in here and say, well, 30 times 3 is 90, so y would be 90. Okay, so we can do that. That's fine. But here's what I'm going to do, because there's still other relationships that are up here. And some of these relationships are better than others. Look at those two. Can I say y plus x plus y minus x equals 180? Now, why is that equation better than any of the other ones that we've created? The other ones are true, but what happens here with those? They cancel out. I'm left with 2y equals 180. Now I don't have to use substitution or elimination or anything like that. I get y to be 90. And if y is 90, now I come back into any of these other equations that I used to generate this, or any other, I guess not generate, but any other equations that were true in my picture, and I can find x. Okay, so again, you're going to see x to be 30. Same thing here. So what I'm trying to get at here is you might do something completely different than your neighbor, because you might see relationships that are different than your neighbors, but at the same time, you should, as long as your relationships aren't contradictory, you should both still come across and get the same results. So this one here, what I like to do, I guess, before getting this one is I like to write all my relationships down and then analyze my equations. Say, okay, well, which ones work best together? Are there any that a variable disappears in, so I don't have to use a system, and use elimination, substitution, that kind of stuff. So when I look at this one, I'm going to use these two to be vertical, so I can say y is equal to 2x. That's one equation. Okay. I'm going to look at these two and say that y plus x plus y plus 5 equals 180. So just adding those two angles up using angle addition. So that's my second equation. And my third one, I'm going to look at those two. So I'll say x plus y plus 5 plus 2x equals 180. Okay. Looking at this, like none of my variables really cancel out. If I rewrite this one, combining like terms, I get 2y plus x equals, if I move that 5 to their side, equals 175. Here I get, what, 3x plus y equals 175. Okay. So what I'm doing there with those two is I'm just trying to organize them in what we refer to as standard form in algebra, which was ax plus by equals c. So I'm trying to do that, and I don't really care if the x's or the y's come first, but I'm going to set them up this way. Okay. Now I could still use equation 1 if I want to, and I think equation 1 is probably going to be a benefit to me. But I'm going to try it this way, just to prove that this can be done. If you remember this process, we have two equations that look this way, and I need to get something to disappear. I want to add straight down, but I need to add to where either the coefficients for y's or the coefficients for x disappear. So what I need to do is multiply this one by a -2. So you negative 2y, this will turn into negative 6x, and this will turn into negative 350. So I just distribute a -2 to the whole thing. And now when I add straight down, my y's go away, 0y. So that's eliminating my y. That's why it's called elimination. Add straight down here, it becomes negative 5x. Add straight down here, it becomes negative 175. Now I can divide both sides by negative 5. X then is, so 20, 25? No. So 5 goes in 120 times, and it goes into 75 15 times. So what's that, 35? So X is 35. And then I can use that to find Y. So plug that back in here. I get 2Y plus 35 equals 175. So 2Y, I'll subtract 35 from both sides, so I get 140. So Y will be 70. Okay, so that's the elimination technique. Now, is that the best thing? I don't think so. I think maybe it would be wise to, if I look at this bottom one and this top one. So what this bottom one was, what, 3x plus y equals 175. That's what this bottom equation, number 3, kind of simplified to. If I use equation number 1 with it, equation number 1 is saying y equals 2x. Well, let's replace that y then with 2x. It's still a system. We're using substitution, but you see that it's so much easier to get my x to be 35 using that approach. And if x is 35, I can come back up here to that equation, plug x in, and get 2 times 35, which would be y to be 70 again. So the idea is, if I foreshadow a little bit, and you're going to hear me talk about don't be a robot. Don't do step 1, step 2, step 3, step 4, because that's exactly what we did in class, because it worked for that problem. Because when you get into homework, those steps 1, step 2, step 3, step 4 might be way more inefficient than an alternative. So I like to write all my equations, all my relationships down, and then start to see, okay, which ones, take that 10, 15 seconds to analyze them, because that 10, 15 seconds used in analyzing might save me 3, 4, and 5 minutes in actually computing and doing the actual algebra. So as we work throughout the year, I'm going to do those types of things in class with you. I'm going to write down all the different relationships, and then we're going to analyze. We'll do a little bit of foreshadowing and say, okay, which one's going to be a little bit easier here to work with, because I think that's a skill that all of us can get better at. Even myself, I can get better at. So that'll be something that we concentrate on. You got assignment 2.6 in Math Excel.